Hello everyone, my name is Shahan Islam. Today I am excited to present my project titled Magnetic Levitation, Maglev Elevators, Powering the Future of Urban Mobility. This presentation is for my ASP-AH4UE class, and the date is June 9, 2025. Over the next several minutes, I'll take you through the science impact and future possibilities of maglev elevator technology in our cities. Table of contents. Before we dive in, here's a quick overview of what I'll be covering. So first, we have introduction, then physics application, then big question and rationale, then curricular connections, then implications, then career information, then biography of a physicist, and then lastly references. So on to our next slide, introduction. Let's start with a brief introduction. As our cities grow taller and more densely populated, the way we move people and goods vertically becomes increasingly important. Traditional elevators have served us well over a century, but they come with drawbacks. Energy inefficiency, mechanical wear, and limited speed. Maglev or magnetic levitation technology is now revolutionizing vertical transportation by using magnetic fields to lift and move elevator cabins without any physical contact. Maglev elevators promise smoother, faster, and more sustainable movement through our buildings. In this presentation, we'll explore how maglev elevators work, why they matter, and how they could change the way we live and work in future cities. Physics application. Now let's get into the physics behind maglev elevators. At the core, maglev elevators use the principles of electromagnetism. The main components are superconducting magnets and advanced control systems. Here's how it works. Magnets are arranged so that they either repel or attract each other, depending on the design. This creates a magnetic field strong enough to lift the elevator cabin and keep it suspended in midair, eliminating the need for cables or rails because there's no physical contact between the cabin and the shaft. There's no friction, which means less energy is wasted and less wear and tear on the system. This is a huge advantage over traditional elevators, which rely on cables and pulleys and are subject to mechanical breakdowns. The control systems manage the strength and direction of the magnetic fields, ensuring a smooth, safe ride for passengers. Big question and rationale. The big question I want to address today is, how can maglev elevator technology address urban mobility challenges while minimizing environmental impact? This is an important question because as our cities continue to grow, we're facing more and more challenges with moving people efficiently and sustainably. Traditional elevators are limited by their speed, energy use, and capacity. Maglev elevators offer a solution by being faster, more efficient, and more accessible. They can move people and goods up and down the building with less energy, less maintenance, and fewer breakdowns. This is especially important for cities with tall skyscrapers, where vertical transportation is a critical part of daily life. By reducing energy use and emissions, maglev elevators can help make our cities greener and more livable. Supporting research, Article 1. Let's look at some of the research supporting the development of maglev elevators. The first article I reviewed discusses how maglev elevators use magnetic fields to move the cabin, eliminating friction and mechanical wear. This is a game changer because it means the system requires less maintenance and is much quieter than traditional elevators. The article also highlights how this technology can reduce energy use since there is no friction to overcome. In addition, maglev elevators offer smoother rides and more flexible building designs. For example, because there are no cables or counterweights, architects have more freedom to design skyscrapers with unique shapes and layouts. This could lead to more innovative and more sustainable urban environments in the future. Supporting research, Article 2. The second article focuses on regenerative drives in elevators, which are closely related to maglev technology. Regenerative drives captures energy during braking when the elevator slows down or stops, and reuses that energy to power other parts of the building. According to the article, this can cut building transportation energy use by up to 70%. That's a huge improvement over traditional systems, which simply waste this energy as heat. The article also points out that these systems are important for green building design and sustainability. By combining maglev technology with regenerative drives, we can create elevators that are not only faster and smoother, but also much more energy efficient and environmentally friendly. Critical analysis. Now let's take a step back and consider who is affected by these developments. Urban residents stand to benefit the most, as maglev elevators can make daily life in tall buildings more convenient and comfortable. People with mobility challenges, such as those using wheelchairs or walkers, will find it easier to move around since maglev elevators can be designed for greater accessibility. City planners and architects will have more options for designing buildings, and the environment will benefit from reduced energy use and emissions. So what is being done right now? Maglev trains are already in use in several countries, and research into maglev elevators is ongoing. Companies and universities around the world are working on prototype and pilot projects. However, there's still a lot of work to be done. We need more investment in research and development, greater public awareness of the benefits of maglev technology, and more pilot projects to test these systems in real-world settings. Curricular connections. Let's connect this topic to what we've been learning in our physics class. The main curriculum expectations that apply here are forces in motion, energy and momentum, and fields. For example, the magnetic force that lifts the elevator cabin is given by the equation F equals Q VB, where F is force, Q is charge, V is velocity, and B is magnetic field. This equation helps us understand how strong the magnetic field needs to be to lift the cabin. We also need to consider energy conservation, which tells us that the energy we put into the system should equal the energy that comes out, plus any losses. In maglev elevators, because there's no friction, losses are minimized, making the system more efficient. Finally, the concept of field, specifically magnetic field, is central to how maglev technology works. Sample problem. Let's work through our sample problem to see the real-world impact of maglev technology. Suppose we have a traditional elevator that uses 1 kilowatt-hour of energy per day. A maglev elevator, on the other hand, uses only 0.5 kilowatt-hours per day. This is a conservative estimate based on current research. Our goal is to calculate how much energy is saved by using a maglev elevator instead of a traditional one, as you can see through the work on the slide. Here's how we solve the problem. The energy saved per day is equal to the energy used by the traditional elevator minus the energy used by the maglev elevator. That's 1 kilowatt-hour minus 0.5 kilowatt-hours, which equals 0.5 kilowatt-hours saved per day. To find the percentage of energy saved, we take the energy saved divided by the original energy used and multiply it by 100. So 0.5 divided by 1 times 100 equals 50%. That means maglev elevators save up to 50% of the energy used by traditional elevators each day. Over time, this adds up to significant cost savings and a much smaller environmental impact for buildings and cities. Implications positive. Now let's look at the positive implications of maglev elevator technology. For the environment, maglev elevators mean lower energy use and reduced emissions, which help fight climate change and make our cities cleaner. For society, these elevators improve accessibility, making it easier for everyone, including people with disabilities, to move around tall buildings. They also provide faster transport, which can save time and reduce congestion in busy urban areas. For the economy, maglev technology creates new jobs in technology, engineering, and construction, helping to drive innovation and growth. Implications, negative. Of course, there are also negative implications to consider. The initial costs of installing maglev elevators are high, since the technology is still new and requires specialized materials and expertise. There may also be an issue with material scarcity, since some of the components, like superconducting magnets, are expensive and not always easy to obtain. Finally, there are technical challenges to overcome, such as ensuring safety and reliability in real-world conditions. Despite these challenges, the potential benefits are significant, and ongoing research is helping to address these issues. Solutions. So how can we address these challenges? One solution is to invest in research into alternative materials that are more affordable and easier to obtain. Another is for governments to provide incentives for green technology, such as tax breaks or grants for companies developing maglev systems. Finally, public-private partnerships can help bring together the resources and expertise needed to build and test new prototypes. By working together, we can overcome the current barriers and bring maglev elevator technology into mainstream use. Career information. If you're interested in this field, there are many exciting career opportunities. One option is to become an electrical engineer, specializing in maglev or transportation technology. To pursue this career, you need a bachelor's degree in electrical engineering, and possibly advanced degrees or certifications. Key skills include problem solving, teamwork, and a strong understanding of electromagnetism. Job possibilities include research and development, urban planning, and infrastructure design. Working in this field gives you the chance to be part of shaping the future of our cities and making a real difference in people's lives. Biography of a physicist. Let's take a moment to recognize the contributions of a pioneering physicist, Dr. Xian Wu, also known as the First Lady of Physics. Dr. Wu was born in 1912 in Lihong, China, and moved to the United States in the 1930s to pursue her education. She earned her PhD in physics and went on to become a leading experimental physicist at Columbia University. During World War II, she worked on the Manhattan Project, contributing to the development of atomic energy. One of her most famous achievements was the Wu experiment, which disproved the law of parity conservation in weak nuclear interactions. This was a groundbreaking discovery that changed our understanding of the fundamental laws of physics. Continue. Despite her many accomplishments, Dr. Wu faced significant challenges as a woman and as an immigrant in a male-dominated field. She was often overlooked for major awards, including the Nobel Prize, even though her experimental work was critical to the discoveries that earned her colleague the prize. This is an example of what's known as the Matilda effect, where the contributions of women in science are under-recognized. Dr. Wu's legacy continues to inspire new generations of scientists and engineers. Her work has a lasting impact on technology and material science, including the development of advanced materials and technologies that are relevant to Maglev systems today. These are my references, and thank you for listening.